Get yourself a little more. Put some sand in your shoes and make yourself a little more loose. Make a hole in a wall. Get yourself a little more.
Good evening, folks. Good evening. Thanks for joining. Okay, I broke a promise from my previous stream. I think I said that I was not going to muck around with my configuration again, yet I have done for a couple of reasons. Partly, one of them is that I got a new monitor and I decided to muck with the resolutions. Hey, Brent Cooks here. Thanks for joining in, mate. Good morning. Must be pretty early over there. It was this or Deep Space Nine. Thanks, Wolf. Cool. Haxothermic, thanks for listening, man. Hopefully that wasn't too painful to listen to. At first I didn't think that we were recording off the bat, and then I realized that we got well and truly into the conversation on that podcast, and we were indeed being recorded from the beginning, but that's cool. I don't think I said anything too incriminating leading up. So could I please get those people who are currently listening to just make sure that the volume of the microphone is coming through clearly enough and that you can hear the music in the background, but it's not so bad? I could be a bit louder. Okay, the mic needs to be louder. Okay, one option then I guess is I could probably reduce the volume of that a little bit, and let me just bump this up a little bit more. How does that sound? Is that better? The wonders of modern technology that I still haven't figured out how to use better. Lord Flippo, greetings, sir. How's it going? Okay, so does that sound good? We're all happy? You should still be able to hear the dulcet tones of Guy Baroni in the background, the man himself who has made it clear that I'm allowed to stream his content while in the background while doing these live streams. So thanks again to that man. So if we've got no more gripes or complaints from people, then I will start to move forward with the stuffs. Okay. Righto, I'm going to flick this over to, where are we? Here we go. Can everyone see that? I should be able to see my Linux machine with a web browser open. Hey Vikrant, how you going, mate? Thanks for joining in. Okay, so I was intending on streaming some stuff last week, and that didn't go to plan because I had a bunch of other things come up and stop me. But what I was intending to do was pick a binary from pwnable.tw, I think. Pwnable.tw. I was just going to pick a random binary from this site, and then somebody who I can't remember pointed out that the rules here state not to share the flags and don't share solutions. So I thought, I don't want to break the rules, so I'm going to avoid this completely. And then a different person, again, who I can't remember, that I will dig up and give credit to, suggested that I come to this site where there's an archive of CTF challenges and we can, pick one of these. There's public write-ups for most of them, so, hopefully we're not annoying too many people in the process of trying to break them. So I literally picked one at random, deliberately not in the easy category, and basically slightly harder than easy because, reasons I don't want to feel stupid. So I decided to pick this one. I chose this one because there were already a number of solves. It wasn't the first in the easy list, and getting access to the content was pretty trivial. Getting access to the binary was really simple. So what I've done is I basically downloaded that and got an environment set up that we can use to play. So what we're going to do is we're going to aim to own this thing. We're going to try and get this CTF challenge nailed. I don't really know what's involved. I haven't really played with it at all. I'm flying blind. And the aim is, as always, for you guys to get a kick out of watching me fumble through the different parts of the challenge in the hope that we can get shells and flags and whatnot at the end of it. I like to run these as fairly interactive sessions. The regulars who are on the stream will know that already. So if you do have questions, then please ping me as soon as possible. I've got the chat window open. Hey, Blue Pill. I've got the chat window open and I will do my best to respond, making sure that I answer questions as best I can. There should be some other people in the chat who are just as, if not more knowledgeable than I am. So please keep your eye out for their responses as well, because I'm pretty sure that you'll get as fast, if not faster, responses from them as you will from me. And they're all really good people. So keep the discussion going, because that's a huge part and parcel of what we're doing. I have said in my beginning previous streams, I now accept donations from people if they see fit. That is a voluntary thing. It is not forced, so don't feel obliged. But if you feel like buying a coffee, then that'd be awesome. Thanks very much. And I won't say any more. Okay, so what I'm going to do is I'm just going to show you what I've got set up here. What we've got is I've got this diary executable, and I've got this exploit.py, which is set up so that the Python script uses Pwnetools to automate the launching of diary and attaching it through a TMUX terminal window. So this is the classic sort of setup that I like to use when I'm having a look at Linux-based binaries for mucking around. And so if I run this exploit script, it should kick things off, and basically you can see what's happening here. This top window here is where the program's actually running, and down here we can see that GDB has attached and the program's actually running. So that's all I've done there. That basically means that we can skip the process of going through the boilerplate. If there's any questions about what you can see on screen over here on the right hand side, then please let me know. So over here in my Windows 10 VM, I've also got this open in two disassemblers. I've got it open in IDA, and I have it open in Binary Ninja. And what I like to do is kind of jump a little bit across the two so people can get familiar with what the tools look like and how they kind of differ. I like them both for different reasons, and so I use them in conjunction with each other. So I've got that diary exploitable binary sitting on disk here in this Windows machine, and that's what I'm using the Win 10 machine for. Here is purely as a tool for browsing around inside a disassembler. For anyone else who is not a regular listener or hasn't looked at any of these streams before, you must know that hacking without tea is very uncivilized. So make sure you have a cup of tea. It's got to be tea. It can be green, it can be black, it can be white. It's got to be tea. I'll accept coffee. I'm okay with water. V is completely out. No V. V is unacceptable. So tea, then coffee, then water, and if you're unsure, then please let me know, and I'll happily lambast you in front of everybody, telling you how bad your drinking decisions are in life and how you can improve them. I guess that makes sense. That makes me the dog, as per your. I doubt that very much, Atwolf. I doubt that very much. Okay, so I will be chowing down on my tea as we go. I also have some dark chocolate here. So, dark chocolate. Hey, Blue Pill, you say I stream on meth. Technically, dark chocolate can be considered meth, although that's probably a little bit taboo, isn't it? I'm just breaking some more dark chocolate off now because, it's good stuff. This is 90%. I'm a fan of the old 90% because it's not too sweet. Good stuff. Okay, so what we're going to do to start with, we're just going to run the diary binary straight up just to see what it does. And by the looks of it, it does exactly what it says on the tin. Ooh, hey, Tan's on the stream. Wow. Dude, it's lovely to see you. For those people who aren't familiar with Tan, he goes by the name Tarnacious. He's a very dear old developer friend of mine who now has departed our shores in Australia and lives over in Europe. recently become a father. It's lovely to see your name in the list there, my friend. I hope all is well and that mum and bub are doing good too. That's fantastic. And in that case, a fresh strawberry milkshake, I think, is more than acceptable. Okay, so this thing looks like a classic sort of add a diary entry, show a list of diary entries, you know, delete diary entries, that kind of stuff. So let's see what this register thing does. Input a date. Oh, I hate typing dates. Let's put in, let's not put that in. Clearly I need to put an unlock on. 1983/12/10. Content size. Okay. 200. Let's say 200 bytes. Please write what happened. Not a great deal. To be honest, I don't know what happened on that date. That's a random decision. 2. Okay, so show entry. Input date. Really, I have to choose a date? I have to actually write the date? Why can't I write 01? Let's do the copy and paste thing. There you go, not a great deal. And I'm assuming that we've got to do the same. There we go. So yeah, nothing particularly special going on there. I wonder what happens when you collide dates. Let's do another register and we'll do the same one. It already exists. Okay, so let's do it the following day. 200 bytes again. Okay, so there's 2 there. All right, let's do the classic sort of what happens when we try and overflow something. Let's go with, we'll register a new one. We'll choose a different date. We'll put a content size of 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, followed by that. Ooh. Okay, that's interesting. So what I'm guessing has happened here is it's accepted the first 10 characters, and then the rest of the input that I've given it may well have been interpreted as the next bit of input that is used to read the selection for the menu. And my guess here would be that I've entered a character when it's expecting a number and it's just bailed on me. So if we run it again and like did that, there you go. So I'm pretty much, I think it's fair to say that if you put letters in for input here, it's not going to be happy. All right, so there's nothing particularly special going on there. Let's just go and have a look at what the application does. So I've got this view in Binary Ninja, and this is the start/entry point of the binary inside Binary Ninja. So as we can see straight up, it's a 64-bit binary, given the use of registers like RDI, RCX, R8, RSP, etc. And let's jump straight to main. Now I've configured this already to show the addresses of stuff, along with the assembly, the hex instructions, because I just like to have visibility of that. Okay, so let's just have a bit of a browse around and we'll see what's going on. Here we can see it's just spitting out a message saying welcome to the diary service. Then it's rendering the menu and it's calling getInt. I wonder if getInt is doing what it says on the tin. Let's have a look. So the body of getInt says, let's go and read some information from standard in and call fgetS. So fgetS reads directly from the file pointer that is specified as part of this argument. So you can see standard in is being passed to fgetS. And then what is it saying here? RDI and ESI. Now I can never remember exactly which way around 64-bit parameters are passed to function in 64-bit Linux applications. So let's have a quick look. I'm just Googling this. Oh, I should do this on screen, shouldn't I? Let's go back over here and we'll go x64 assembly pass parameter. or something along those lines. Let's just have a quick look. Another tutorial, passing parameters. Let's just see. Already mentioned blast, what do you want to know? That doesn't look very helpful. Tell you what, when I'm inside a virtual machine, the scrolling of the mouse wheel is terrible. I'm just going to quickly take my jumper off because I'm actually really warm. Okay, sorry about that. Must be the tea making me nice and warm. So someone in the chat might want to say, hey, this is the order of the parameters. Sorry mate, any chance you could link the binary in the chat? I most definitely can, sir. 1 minute, and I will do exactly that for you. So, where is it? Is it this one? I think it's this one. Diary, where's diary? Here it is. Attachments. Yep, there it is there, I think. So I will link this, paste that in the chat. There we go. Justin had a cheat sheet. Yeah, I know. And the funny thing is it's actually quite annoying because the way that parameters are passed in Linux on 64-bit are slightly different to Windows, I believe. So I can never remember whether in Windows I think in Windows it's RCX and RDX first, and in Linux it's RDI and RSI. We can probably infer that from looking at this, right? So there's no mention of RCX here. Excuse me. Now we know that the fgetS function, actually, you guys might not know, fgetS takes 3 parameters. It takes in the file pointer that you want to read the data from. It takes in a pointer where the data is going to be written to, and it takes a size as how many bytes it's going to read from that particular file. And it's one of those functions that decided to go completely arse about face compared to other ones and have the parameters in a strange order. So here you can see the first parameter is a buffer to where things are stored. The second is the size, and the third is the file stream that we're reading from. Okay, so that would mean that I would assume this to be like RSI or RDI. This would be the other one, and then this one here would most likely be RDX. So going back over here, we can see we're putting standard in RDX, we're putting 20 in ESI, and we're putting what clearly looks like a buffer in RDI. So I think what we can infer here is RDI does indeed take the first parameter, RSI is the second, RDX is the third, and maybe RCX would be the fourth if there was another parameter. And then so from there, once we've read that value, once we've read that number of bytes, which is only hex 20 or 32 characters, we then take the very same buffer and pass that to Atoi, which converts the content that's passed into an integer. And if that fails, then the value returned is 0, I believe. Let's check that. Pretty sure it's 0. Return value, there you go. This function returns a converted integral number as an int value. If no valid conversion can be performed, it returns 0. So there's our answer. That would explain why when we run this and we pass in something that is not a number, we end up with 0 coming out, and 0 says to exit the program. So that makes sense. So getInt does appear to be doing exactly what it says on the tin. Detective Sars, I know as much as like the average person knows. Ah, fantastic. That's probably slightly more than the rest of us, so prepare for some questions. I don't know anything about computers, so I'm learning from this. Hopefully we're all learning something from this, mate. That's the point, but be sure to sing out if you have any questions. What else have we got? Foob, RDI, RSI. Thank you. There we go. That's very helpful. I just failed at Googling it clearly. Vikrant, any particular reason you don't do the man sections for those glibc wrapper functions? Just asking. I find using man pages for this stuff to be a little bit tedious, and particularly on stream. I like to have a, let me just show you how I Google for stuff and where I get the answers from. And I find that it's pretty easy to digest what we're seeing on screen here, rather than seeing it laid out in a console. Here we get nice syntax highlighting and examples, and it's pretty clear what the sections look like, whereas man pages are not quite so clear. So that's just my personal preference for the sake of streaming. Lucas, when you say the order changes between Win and Linux, is that compiler decision? That's a really good question, mate. No, actually, I don't think it is a compiler decision. I think that's a Windows decision. But I'm not exactly sure. I think we might even come back to that and talk about that again a bit later on, because I'm interested to know what the motivation for that is. But I'm pretty sure that it's just, Windows and Windows API and whatnot have decided that that's what happens when you call functions. But yeah, that's a really good question. I don't know the answer off the top of my head, so we will have to address that in the future. Okay, so let's go back to the body of this function and let's see what it is that it's doing. So once we've read getInt, we compare it to the value of 1, and if that is correct, i.e. if it is 1, then we call register entry. Okay, after that, what do we do? If that fails, then what do we do? If it's greater than 1, we then go and compare it to 2. And if it's 2, we call show entry. And then we check again. If it's not 2, we check see if it's 3. And we call delete entry if it is. Otherwise, we end up going wrong input and looping. Whereas over here, if it's not greater than 1, i.e. it must be less than 1, then we'll consider that to be a 0 and bail out. Call exit and we're done. Okay, so that's not particularly confusing. Nothing particularly surprising going on there. It would be OS API, in fact, for the res parameters. Yep, thanks Vikrant. It makes a lot more sense for it to be that way rather than compiler specific. I mean, thinking about it again, if it was compiler specific, then all compilers on Windows would have to do exactly the same thing, which clearly they do. But yeah, I mean, yeah, you wouldn't really make that an option in a compiler. It would be enforced because the operating system would require it. Otherwise, things just wouldn't work as expected. So, yeah, cool. All right, let's go and have a look at what happens when we do more stuff. We'll go to register entry and have a look. Okay. So when we call register entry, obviously we're passing this string to puts to say, give us some information about this diary entry. And it looks like there's a helper function that reads dates. Now, what does this do? Okay, we can see here it's just using scanf to read 3 values and probably doing some basic checks in here to make sure that the values we give it aren't invalid. From what I can see here, I'd be very surprised if there was some kind of bug in here that would be worth looking at / exploiting. Because at the end of the day, I would assume that whether the date's valid or not, it's just storing that as an identifier somewhere. That would be my assumption at this point. So, but I have been known to be wrong on many an occasion. There's a good chance that I will be wrong again. So I'm going to go on with that assumption, though, that the actual value of the date doesn't matter too much. And we'll revisit that if I prove to be wrong a bit later on. All right, so we input a date, and then what are we doing? We are doing a check, and if that check fails, we end up at the bottom of the function. And okay, so The result of input date is returned in RAX, and here is a lovely compiler side effect where we store the result in a local variable and we read it out and back into a local variable, which clearly we're using later on anyway. And we test to see if that actually worked. And if it did, then what are we doing here? We're checking another variable to see whether or not it has a value in it. So this might actually be checking to see if various components of a date are valid. Let's just have a quick read. So when we call input date, what are we giving it? We're giving it this variable here. We're saying read in only hex 20 bytes. No, sorry. That is absolutely incorrect. Let's go back to input date and see what it does. I'm probably just getting ahead of myself. So we are reading. We are passing in input date. Oh, okay, so it looks like there's different messages. Okay, we can see that we do actually get different messages displayed depending on a value that was passed in, unless this is somehow global. It looks like it is. Aha! Would you look at that? So what I can tell here is there is this global variable which has a flag in it, and it looks like it starts off as 1 or true. And when we look at this code here, input date says check to see if that global variable is set to 1. And if it is set to 1, then the first thing we do is set it to 0. And the message that we output here is input date, and we give it more information, as in we specify the range. But then the next time this function is invoked, it comes in here and checks to see if that global variable is set to 1, and it's no longer set to 1, so all it says is input date. So at that point, clearly it's assuming that you know the format that it's expecting. So, null mode. Hey mate, how you going? Lovely to see your name in the list. If you click on the jump line, does it jump to the location? Yes, I think it does. Let's give that a spin, shall we? Yep, there we go. So if we do that, it will take us to where that line goes, which is down here. It doesn't seem to highlight it though. I think it does in IDA. Let's have a look. So if we go like this, yep, there we go. It does remain highlighted very slightly. So you double click, it takes you and the line stays highlighted. So IDA does have that feature, but Binger doesn't have the line highlighted, which does make it a little harder to read, but it's, I still think, quite digestible. Yeah. Yeah, Koilen, there are two. This one here is called Binary Ninja, and the one that we're looking at over here is IDA Pro version 6 point something, because I haven't updated my license to include for version 7. Okay. Any questions so far? I hope you'll sing out if you get stuck. Okay, so from here, what are we doing? We've got 1, 2, 3 variables which appear to be located. What's this? RBP 14881C. So we're clearly storing stuff on the stack, and we're reading 3 integers according to this. %d/%d/%d. Now, those 3 integers, where are we storing them? So scanf takes what? It takes what is the first parameter scan? It's just the format string, isn't it? Yeah, it's the format string. Scanf takes the format string first, which would be in RDI, or in this case it's being set in EDI. And then from there, for each one of the values that you're reading, you're specifying a buffer that you want to write that stuff to. So what do we got here? RSI would be the next one, var24, followed by RDX var20, followed by RCX FRC. Is that what was set up here? Yep. RDR, RSI, RDX, RCX. So there you go. Parameter 1, parameter 2, parameter 3, and parameter 4. Okay. Yes. How interesting. So given that that's the case, oh yeah, that is exactly right. So 1, 2, 3, and 4. So we read 3 variables in, and then after that, what are we doing here? We're saying look at what would be the year and compare the year to 7B1, which I would assume is probably something like 1970 or something similar, right? Let's do something semi-useful here. OX7B1, is that what it was? 7B2, 1970. It was 7B1. Okay, so it's checking to see if it's 1969 or lower, I would assume. And if it is greater than, then we jump to 145F. Let's compare that to that. Oh, sorry, I skipped one. If it's less than or equal to 1969, looks like we bail out. And then we check the year again, and we check to see if it is greater than 7E0, at which point we will bail out again. So let's see what that is. That's 2016. So this was obviously hard-coded for a couple of years ago. And then what are we checking? We are checking the month. So we're checking if it's set and if it's greater than, what is that? ABC 12. So that's 12. If it's greater than 12, we bail out. And here we're going 1C, which is the day, which technically is a little bit more convoluted, but here we're checking obviously just for 31. Now I wonder if it's going to check to see if certain days are valid compared to other ones. Let's have a look. So if we add a date of 1977, well, month is 12, and let's set, actually no, not 12, sorry. Let's go the 31st of February, which we all know is invalid. There you go, so it's quite happy with it. So there is no 31st of February ever, but clearly it's happy with it. And you know, for the sake of a CTF challenge, you can't exactly blame them for not taking the steps to go to the nth degree and making sure that the dates are actually valid dates. I mean, at the end of the day, they're just an identifier. So what's interesting though is like how are they returning those values out? R1C. So I would assume this means that when things are valid, we jump to here, and when they're invalid, we go through and it looks like we set these values to 0. So maybe what we're doing here is when this function is called, we're actually passing values in on the stack, which are pointers to where these values are going to be stored. I think IDA actually does a better job of visualizing these. I'm just going to quickly jump over here and have a look at input date. Let's see. Nope, I am wrong. It doesn't say anything here, does it? Let's go back to register entry and see what it says here. Input date. Call input date. Maybe it actually returns a pointer in Rex. Let's see. This is interesting, isn't it? It looks like it's actually returning a stack pointer that contains the variables. So where are we? We call input date here, and we store that pointer in here. So it looks like the pointer that's coming out is a pointer to some block of memory that contains the values for the dates, and we're just retrieving those directly. Anyway, so what's clear is we're able to read a date. We get some kind of identifier for it. And then we allocate some memory. This is interesting. So we allocate a fixed size of hex 20 bytes, and RAX is stored in a local var. So I'm just trying to fumble my way through and understand what this means. It looks like the first thing that we're doing is checking to see whether the inputted date exists. So, EDI. Okay, I see what's going on here. So we allocate 32 bytes, and we're basically writing information into that allocated memory. Oh, no, we're not. No, we're not. Don't listen to a word I'm saying. We are not doing that at all. We are reading values out and passing them into this find function. Now let me just see what this looks like in IDA. So I'm kind of hoping that IDA is going to do a better job of recognizing the parameters that are passed in, but clearly it isn't. So we'll go back to Binger because it's a little bit nicer on the eyes. So we call find, and I would assume you're giving it either one string or 3 parameters, and that's basically used as an identifier to see whether or not the entry exists somewhere. I would assume that there's some global pointer somewhere. Hey Wyagul, thanks for joining in, mate. Long time no see. Hope all is well with you, mate. Okay, so let's have a look. At the start of find, first thing we do is we go and grab a reference to something that's clearly a global variable. And this global variable is stored up here. So once we get that value out, we store that in a local variable. And then what are we doing here? We're comparing the value that we got from this global variable to this dtop. Now what's dtop? This is another global. So by the look of it, this dtop, I would assume, is probably going to be some kind of global pointer to a list of diary entries. That's what I would assume it's going to be. So dtop being the top of the diary entries, perhaps the head of a linked list or something similar. And you can see here it's 1, 2, 3, 4, 5, 6, 7, 8. So that would be a pointer's worth. I don't know what this would be. But I'm interested to know what this actually says. I mean, this points to this, like that's a hard-coded value pointing to this. Okay, so what's clear is it's saying if we've got a hard-coded value here that points to this, and that's how things are initialized, then when we go back over here and we see the code that says compare this value here to dtop, then you would assume, given that this begins with a hard-coded pointer to dtop, that those values will be equal. So if they're equal, we end up skipping this stuff and going all the way down to here. Okay. Now, what that says to me is, I mean, if you have a look at the body of this code here, there's this compare date call, CMP date. I'm assuming it's compare based on its name. And by the looks, there's a loop. So it's comparing dates. It looks like it's actually going from the start pointer, which is in dtop, and looping continually through and comparing dates. And if it finds one that's the same, then, sorry, if we find one that's greater than, and what are we doing here? We jump from here to this line of code, which is where we originally jumped from. And then we then compare what the current iterator pointer is to dtop. And if they're the same, where are we going next? We are jumping all the way down to here and returning 0. So we set EAX to 0, the return value to 0, and then we bail out of the function. But if we find, looks like if we find a value that matches based on this date comparison function, i.e. if we continue to go through and we end up finding something that's the same at this point here, then it looks like we instead return whatever that pointer happens to be. Okay, so my guess would be that find returns a pointer to the element in the global list that matches the date that we've specified. Which, you know, when you look at the name of the function and have a quick scan over the body, it's probably pretty obvious that that's what it's doing. Okay, so let's go back out to where find is invoked. Okay, so if we call find, we check the value of REX, and if it's non-zero, it means that the pointer that was returned is a valid pointer, you would assume is a valid pointer, or is a pointer to an entry in the list. And here you can see it's saying, oh, it already exists, i.e. we've specified an entry with that exact date. And then what happens? What are we doing here? Excuse me. We are freeing up the memory that we allocated here. And then I assume we finish up. Yes, we do. We finish up and we end up going back to the start where the menu loops. So let's do this again just to prove it. Register that input date and we're back to the beginning again. So that's us hitting this already exists sign here, and then back we go. Okay, so assuming that we have specified a date that doesn't exist, which is a condition that arises when the list is empty and when it's iterated through all of the list entries and nothing's matched based on the date comparison. We then go through and we do this block of code here. All right, so quick recap. That's probably actually worth checking again. When we go into find, there's this compare date. It looks like it's not just doing like a straight string comparison in here. It looks like it's doing a component-based comparison. And I would assume that the reason that it's doing that is to make sure that the comparison returns whether or not one date is greater than or less than or equal to the other date. So by the looks of it, you can see here we're returning 1 in some cases, -1 in others, -2 in others, +2, +3. So there's a bunch of different conditions. So my guess would be that they're looking to use something like -3 for year. If you return -3, that says that the year is less. If it was +3, then the year is more. -2 might be month less, +2 month more, etc., etc. That is purely based on speculation. And the reason why I say that is because a lot of comparison functions that are built into libc return either -1 or +1 depending on whether one thing is greater than the other or not, or 0 if things are exactly the same. I think this is sort of taking that to the next level and only returning 0 when they are exactly the same, as we can see here. Whereas for any other case, they're trying to indicate which component of the date is greater than or less than. But that might not necessarily be interesting for us as from an exploitation point of view. All right, so what happens here? We then, once we've read in this input size, we're calling getInt again. So we read in an integer size value, and that looks like it's stored in bus. I'm going to start modifying these variable names. So we'll call this content size so that we can see that throughout our code. So here we can see we're reading in the content size, and the content size is stored here in EAX. That's then copied over to RDI, which we know is the first parameter to a function call in 64-bit Linux. And here we allocate memory. So we're literally doing a malloc, which is directly mapped to the same size that we have specified. So it looks like it's just allocating a block of memory based on our input, and maybe not storing any metadata alongside it. So what do we do then? What is this var10? Where are we using this? This looks like it is it's a pointer to this block of memory that we allocated up here. I wonder what this is used for. Not immediately clear to me at the moment. Feel free to offer some insights if you guys have any ideas. What are we doing? Let's have a look. So looks like it's doing some basic doesn't look like it's doing anything particularly special, really, is it? So we've got another helper function here called getNline, which if we were to go based on the name, it would be saying get a line of characters up to a certain length. So for example, looking again at the classic naming conventions in libc functions, things like strncmp or snprintf. Every time you see an n, you sort of specify the length of a particular thing. So perhaps this function here is saying go and get a line of information from the console that makes sure that it's no bigger than what we've specified. So again, if we have a look at the parameters that are being passed in, what we're saying is we're giving content size as the third parameter. We are, what are we giving this var_10, which is a pointer to what? The date? Where are we? We store, this is that block of memory again, isn't it? var10, var18, we're storing var18, which is the date. Yes, so we are storing the date in this block, which means that looks like we're reading date components out of this block. And we're reading more out here. Yeah, okay, I see. Yes, please write. Okay, so this is just displaying the date inside this printf. If we looked at this string, what have we got? Please write what happened on. There you go. There are the components there. So it's expecting the 3 date components, and that's what we're extracting here out of this var10. So this, I'm going to rename this. Go inputted date, so that we know that that's actually a pointer to something that contains the inputted date. Okay. So we print that out, and then we say, what are we saying? We're saying get nline, and we are passing in what are we passing in? Size. Starting to think that variable is used for way more than what we expected. So rax rdx. Yeah, okay. rax, there we go, that's it there. So this is, I'm just going to document this here just a little bit. We're going to add a comment that says store allocated memory in a local variable, just so that we know. And here where we read it out again, which is rax plus 8, and rax, as we know, is based on this inputted date pointer. Okay, so same story here, rax plus 8. So rax here now contains the allocated memory. Get the allocated memory pointer. Okay, and here you can see rax is being passed in as RDI. So first param equals pointer to memory. So I'm just going to put that there so that we know that when we call get endline, the first parameter is the pointer to the memory, and ESI, which is the second parameter, has this content size in it. Okay, so second param equals size to read. Okay, any questions? I'm hoping this is pretty standard. I'm sort of documenting this in my own way because it helps me understand what's going on. Every time I go back, I feel like I've kind of lost track. So adding those little comments and renaming things along the way tends to help me. Hopefully they'll be helping you as well. So get endline, let's have a quick overview. You can see we're calling read, which is interesting. So we're not using fgetS or anything like that. It's actually reading everything. So that would mean that if we were to put data on the wire, we could put any bytes that we wanted to at all. So it's not looking for a new line. It's literally reading that many bytes off the wire and writing them directly to the memory location that it has given. But what is it doing here? Is it even, it's not even checking. Let's have a look. When it calls read, it passes in 0 as the first parameter. So for those who don't know, the read function, I'll do what I did before. Let's go to a browser. The read function takes, I think, 3 parameters. Whoops. It's not system calls that we want. It is possibly one of these two. Read 3 parameters. Int file descriptor, a pointer to the buffer that's going to store the data, and then however many bytes to read off the wire. So the first parameter being the file descriptor in Unix land, I think in Windows land too, the file descriptor of 0 refers to standard in, so the keyboard, so to speak, the input from the console. So that would mean here, when we pass in 0 as the first parameter, we are reading data from the console. The second parameter RSI stores this var20, and that would be the first parameter that is passed into this function. And as we have documented here, first parameter is a pointer to memory. So if we go back here, we can say, we'll just call this the buffer pointer. And ESI is the, in fact, we don't even need to do that. Let me get rid of that. var20 is the buffer pointer. And 24 is the buffer size. Okay. So this is interesting. Have a look at this. This is interesting here, isn't it? Buffer size. So we read the buffer size that was given into us, and then we add 1 to it. Read 1 extra character. So that immediately stands out as a potential issue. Does anyone else think that too? Because we're basically saying at this point that we are happy to read in 1 more byte worth of information than we have allocated for. Is that right? Am I missing something? Is anybody else rubbing their heads a little bit there? Hey, Zarubis, didn't even know you dropped in, mate. How you going? Yeah, crazy town. I think this is something that we need to stay focused on. The fact that it's saying read in 1 more byte means that we can we can write to 1 more byte beyond the array, the area of memory that we have allocated. So that smells. There's a smell in there. There could be something in there that we could look to abuse a little bit later on. Does that make sense? Hopefully it makes sense. So anyway, clearly this is reading n+1 characters into a buffer. The result is stored in this var_c, which is just a local variable. Doesn't look like it's being reused unless Yeah, no, it's not. It's not being reused. Okay, so where is this jumping to? This then saying, excuse me, compare. Move what looks to be a value into ECX, compare it to this other local variable and jump if it's less than to here. Okay. Looks like we're doing an iteration over the data that's been read in. And we can see that we are searching for something. We are searching for a new line character. And if we find a new line character, let's go, is the current character a new line? So if it's a new line, sorry, if it's not a new line, then we just basically increment our loop variable and go again. So this would be like I'm going to call this loop index, because that's what that appears to be doing. Sorry, Lurker, mate. I honestly thought I had. So for those people who don't know, Lurker is it was my first Patreon donator and gets special privilege as a result. So he is a top lad, and I should have given him a direct notification, but for some reason I forgot, and I'm very sorry. I'm very sorry. I'll make it up to you, my friend, I promise. Feel free to make up for the lost time with trolls as much as you like. I'm more than happy to receive the trolls. Okay, so clearly we're looking for a new line, and when we find it, we are null terminating it. So overwrite new line with a null byte. So we're effectively terminating the string when we stumble across a new line, which is interesting. Which is kind of unnecessary. I mean, if we were to, as from an exploit perspective, this doesn't mean anything to us, but from a rendering perspective, it does, because if this value, and this value will be later written to screen, then the print functions obviously don't want to print out all the new line and all the other stuff that might come after it. So it's looking for new lines and null terminating it. And this is something that we would probably need to bear in mind for later as well. So if, say, for example, we were hurling shellcode into this function, or we were putting addresses in here or something along those lines, then any of the addresses that have a byte that matches a new line, they're going to get mucked with. So that's something to bear in mind for future, should we need to abuse this facility to read in arbitrary data. Does anyone here want a steroid injection of I won't get involved in that conversation. Okay, so that's all that's doing basically. It's iterating over the data that's been read, and it's going from the start to the end. But if it manages to stumble across a new line character in the middle, it null terminates it at that point. And then what we can see here when it bails out of the loop is it returns this loop index value. So that's telling us how many characters have been read.
Pattern recognition.
Okay. So get endline, we can see here. Get endline. You can see the result of get endline is effectively ignored because RAX is immediately overwritten with a pointer to the input date. So there are two things now that we are doing. We are passing in, what are we? Hang on a second. RDI now contains a pointer to the inputted date, which was from further up, and the pointer to the data that's been written, which is stored in RDX. Rax plus 8. So what was Rax again? That's offsetted from there. Okay, I see. Okay, so clearly what's happening is there's like a block of data on the stack, and that data contains information about the date and a pointer to the associated information that is effectively the content of the diary entry that matches that date, right? So this insert function is only taking one value, which is a pointer to the start of this inputted date. And it looks like it's assuming that the inputted date is right alongside, whether it's in front of or behind of the pointer, that it looks like it's in front. Inputted date is RVP minus 8. Rax plus 8 is RDX. So it looks like the first 8 bytes is the date, and then the second 8 bytes is the pointer to the associated data. Okay, so insert. What does insert do? It's going to be pretty obvious, right? And I would assume that if there is a global variable that contains a list of all the diary entries, then it's probably going to grab a reference to the head of the list. It's going to loop through the list until it finds where it needs to be inserted. And then it will probably insert the value based on a fairly trivial list manipulation function. Okay, so let's have a quick look. Insert. Now we know that RDI contains a pointer to the structure to be inputted. So I'm going to call this the input struct, because that contains the date and the value that we're looking to insert. And next we're reading this global value, which, as we know, begins with a pointer to this dtop. And from here, what are we doing? We are storing that in a local variable, and then we're storing the value of 1 in a different local variable, and then we begin a loop. So we compare the pointer that's stored in data 6020D0 to dtop. So does this global pointer point to the head of the list? I think that's what that's doing. And if it does, then we jump down to here. Okay, so this is the case where we're either inserting for the first time. Yeah, we'd be inserting for the first time, I would assume. So let's for now, we'll ignore this looping here in the middle, and let's just see what happens to begin with. So for the very first time, we know that this is going to be true anyway, because the hard-coded value to begin with points to the head. And when that happens, var10, which is the pointer to this data doohickey. So RDX contains that value and RAX contains the input. And then what are we doing? We are storing whatever that global pointer value is at an offset 16 bytes beyond the input structure. Okay, that's right, because let's not forget that when we had this original malloc, let me just quickly take you back there, we allocated 20 bytes, okay, and we store date-related values near the beginning. Where are we? Rex. That's the inputted date. RDX contains var18, which is the input date pointer that came out of that original function. And then we write all 8 bytes of the date directly into the first 8 bytes of that structure. But there are 32 bytes, so there's 4 more pointers. And we can see when we come down here, we're actually storing RDX which is a pointer to the diary content, into the following 8 bytes. So we've got date followed by pointer to the data, but there's still another 2 blocks of 8 bytes immediately after that. Now, if this is going into like a doubly linked list, then those 2 pointers might actually point to like previous entry in the list and the next entry in the list. I have some Bose Companion 20 speakers and QC35 headphones to send you. Wow, no you don't, my friend. Let's argue about that another time, and certainly not in public. We'll talk about that later. Does anyone have any questions? Does that make sense? So maybe we should comment this just a little bit, okay? Let's say here, store the date in the first 8 bytes. Okay, store the date in the first 8 bytes. And then here, this line here says, store the pointer to the diary entry in the second 8 bytes. Does that make sense? Okay, so we know we've got basically 32 bytes worth of memory based on this. We've chewed up 8 bytes for this date, and then we've chewed up another 8 bytes for the pointer to the content. All right, and then we go to insert, and here we're saying, assuming that it's the very first time. So we've got our struct, and that's in racks, and we've got this local variable, which is what appears to be like a global pointer reference thing. Hopefully that will become more clear. And we're storing that pointer into the next 8 byte block. Okay, so that means that whatever's stored in here, so this initially 6020C0, right? That value is being written to the next 8 bytes. Okay. Nothing like waking up, seeing AJ hacking stuff as I get into work. Aconite, nice to see you, my friend. Waking up, gee, what time would it be there? I don't know where you're based. Actually, I think I do know where you're based. Well, good morning to you. I hope Tuesday is a winning day for you. So, we were here. We are storing whatever the current value of that global pointer is. Clearly there has to be some kind of overriding of that global pointer so that things are updated. So let's see what this is doing. We're storing, I'm going to call it global pointer or global reference in bytes. What are they? 16 to 23. Okay, so like the third block of 8 bytes. And then, what are we doing here? Again, I'm going to call this global reference. I don't really know what this is a reference to yet. It looks like it's being used to track like where the head of a list is or something similar, but I'm really not sure. So then we grab the global reference value again in RAX, and we add 18 bytes to it and read that value out as a keyword. Okay, so that's the final 8 bytes. Okay. Righto, so if we go back here, we can see that this is one block. And then immediately after this, so there's 1, 2, 3, 4, 5, 6, 7, 8. No, that doesn't make sense. Global reference into racks. And we add 18 hex, which is like the third block, and dereference that and read that value out into RDX. Right. So yes, that's exactly what we are doing. Global reference racks. Okay. I think what's going to be clear here is that we will most likely understand things a bit more if we debug as we go. So let's do that, because I think that'll be interesting. What I'm going to do is we're going to go into GDB and we're going to look to see what this insert function actually does, and we'll get an idea of the values that are being read and where they're being written, and that'll probably make things a little more clear. So what we'll do is we'll automate this a little bit to make it a little bit easier for us. I'm going to set a breakpoint here. Copy address. Hopefully copy and paste across my virtual machines will work. So you beauty, they do work. So I want to break there so that we can see what this value is when it first comes out. And then I'm going to break here. Copy address, we'll do the same here. Now if all goes to plan, this stuff will just be nice and smooth. All right, so I'm going to kick off this, I hate that. Kick off this exploit. And there we go, we've got our breakpoint set and we're running. So let's register. I'm just going to use this base date to begin with. We are going to, what are we going to punch in? Let's say something obvious, 64 bytes, let's do that. Nothing happened. Okay, so let's have a look here. What I might do is just maximize that so that we can see without the noise of the exploit in our face. So you can see that we've broken on this move instruction, move the value that is in that global pointer that we found over here, that's this line here, and store that in RAX. So I get my boo happening. So RAX now contains 6020C0, which, as we know at the start, 6020Z0 points to dtop. Okay, so that is our original entry condition. So we're going to just skip over that check for now and go to the next breakpoint. So we'll continue. And so RAX is this pointer to some stuff. Now this pointer here, remember, at this line, RAX keyword pointer RVP plus 18, is this line here. So RAX contains a pointer to the structure. And so RAX here being the pointer. And so the first 8 bytes is the date. The second 8 bytes should be a string that contains what we gave it. So if we went show the string at this plus 8, hopefully, clearly I'm wrong. Oops. What am I, oh no, that's a pointer, right? So that would be, is it QW? I can never remember. Plus 8. No. Is it GW? GQX? No. I can never remember the shortcuts. Ooh, what do we got here? Oh, God. Someone bought me some coffee. Was it you? Man, can't stop the giving, can you, mate? Nothing but a jerk. Thank you very much. It's a very nice gesture. Yeah, someone needs to make a, tea donation facility. All right, let's just stop for a sec. What I want to do is go, where are we? Just want to remember what the format parameters are for this. Okay. Right, 1970. So we're looking at a D word value at the offset. We can see that the year is specified at that point. If we add, what would it be? 4 bytes. So that'd be 8 plus 4, 257. So that's not going to work. We need to, is it a short? How do we do a short? There you go, 1. Okay, so we're basically spitting out a decimal byte there. So we can see that the day is 1. And then if we add 6, we should see, is it 6? Yeah, no, it's not 6. I would have thought that it would be 6. Maybe maybe it's single byte. Yeah, there you go. It is single byte. So that means that the year is stored at the beginning, and then 4 bytes later we have the month, and then 1 byte after that we have the day. And we don't need anything more than 1 byte. But clearly there's like an 8-byte block based on what we're seeing here that that contains the date. So what we need to know is, if we look at this pointer, it's not Q, is it? Is it G? I'm gonna have to Google this. GDB print 64-bit pointer. Sorry, just quickly Googling because this is painful. Where are we? X short p/x. Regard bits as an integer. Print them as an integer. Assign decimal. Looking for sides. G, giant words. So it's definitely X. G. Maybe I gotta go now X, G, GX. There we go. Okay. X, GX, and then +8. There we go. See that? That we have a pointer here. So now if I access that pointer, there you go. Okay, that makes a bit more sense. So sorry about that. I failed to dereference the pointer rather than use it as a string. So we can see that this is the first 8 bytes, and that contains the date. This is the next 8 bytes, which is a pointer, and you can see that that pointer contains nothing happened, which was the diary entry value that we have specified. Okay, so going to the next line, RDX, which points to the original dtop/magic value. Excuse me. That is being stored in RAX +10. Right, so at the moment, RAX, I could probably just specify it here. Remember, RAX contains a pointer to our input structure. So RAX plus hex 10 is null because nothing is in it yet. So we're about to write the value of, what is it, 6020C0 to that location. So that should now be set to this, which is clearly a pointer to this dtop. So maybe our assumption here should be that dtop is just like a terminator pointer, right? So that we can say, you know, are we pointing at the terminator, then we know that we need to stop iterating. So if that's to be considered the next value, then we know that we can assume that as we're iterating along, we hit that as the next value. We basically stop iterating. Okay. Right. So next, RAX now contains that head pointer value, and RDX also contains that exact same value. Okay. So let's quickly go back here. It might be a little easier to digest. We're pulling out the global reference again, and it looks like we're going to be writing something back to that global reference location, right? Because Rax now contains our pointer, our global structure, and we're now writing RDX, which is again a pointer to the terminator, into, we're storing it in 2 locations. We're actually writing that to the 4th pointer as well. Okay, so it looks like we have this hard-coded terminator called dtop. And when we first add an element to the list, then both the next and previous pointers point to the terminator. So maybe this is a way of avoiding like using null as a terminator. But what's clear is if we print out 4 pointers, we can see that like these are the 4 pointers that we've got stored in our structure element, okay? The first one contains the date. Second one contains a pointer to the string that makes up the data. That is the diary entry. The third pointer and the 4th pointer both point to dtop, this thing here, right? So, and as we can see in other areas of the code, we're actually checking to see if dtop is referenced, right? Like here, are we pointing to the terminator? All right, so let me just quickly have a look. So dtop here has, I mean, there's only enough space here for 2 pointers. So maybe there's some assumption that this is always going to be, first of all, a null date, followed by a null pointer. And then from there, because we know we've reached the terminator, that there are no other pointers to reference from that point on. So we don't actually need to have 2 other nulls. But we'll see. Could be wrong. So, we've got more questions. dtop is hard-coded as a global address. Does this change with ASLR or is the binary not compiled? That's a great question. That's something that I've missed. Let's check sec. Okay, so here's your answer, Lucas. We've got stack canaries enabled, fortify is disabled, NX is enabled, and PIE is disabled. So there is no ASLR on this binary, which we can infer just by looking in here at Binger, because these addresses seem hard-coded. There's no sort of relative offset from 0. So yeah, there's no ASLR for this binary, which means that dtop is always going to be the exact same location every time this is run. Does that answer your question? I hope so. Something about banks. Concerns me there. Yeah. Oh, you're looking at news articles. Couples' dreams turn to nightmares. Hackers steal funds. Oh, this is the what was it? The MasterChef finalist who got owned because of some conveyancer using that PEXA platform. Yeah, something like that. Yeah, I got no comments on that at this point. So I'll let you guys continue talking about house settlements, and I will continue talking about ownage. Okay, so moving on, we are storing those 2 pointers in those 2 locations. Now what are we doing? Rax again points to that global struct. What are we doing now? We are storing RDX in Rax plus 10. So RDX, here you can see RDX is being written to a location offsetted from RDX is being written to a location offsetted from RAX. Now RAX is the pointer to, basically the pointer at dtop, and RDX is the pointer to our first structure. So we skip over that. If we look at Rax plus 10, so Rax plus 0, Rax plus 8, Rax plus 10, that now points, so there you go, we can see dtop. Dtop now contains 2 null values and points back to our element. And next, we are retrieving, again, the same 2 pointers, and we are writing that second value again to the end of the list. Right, okay, so our terminating entity, which is dtop, clearly has 2 nulls in it, which I would assume would represent the date being null and a pointer to data being null, followed by a previous and next pointer, perhaps, maybe a head and a tail, perhaps. And so when we look at it here, you can see they're both pointing to the one element that's in our list at this point. Okay, and then what are we doing? We are returning a value of 1, which I would assume maybe refers to the length of the list at this point. Okay, so now what I'm going to do is I'm going to register another one, and this time we'll go do this on the second. We'll do 128 bytes this time, just for shizzles, and we'll pretend that something meaningful happened here. Okay, so now I'm interested in what this insert process is going to be doing this time, just so that we get a bit more of a memory map of how these things are added. So what's clear is that it's creating some kind of data structure in memory. We need to make a point of understanding what that is. So Rex right now, that's pulling out the value of, now let me go back over here. Where was our first breakpoint? It was this. So it's basically retrieving the global sort of head pointer, right? Which we know is our first element of the list. Okay, and we are then storing that in a local variable, and the value of 1 is also being stored in a local variable. And then we start what appears to be a loop. We are comparing that first pointer to the global pointer, which is dtop. And in this case, this is where we are just here. This will now return false, i.e. the jump equal will fail and we'll end up coming into 1228. And we'll be able to see what's going on at this point. Okay, jump is not taken. So RDX is being extracted. RDX it's the local variable. Same with Rax, which is a local. So Rax points to, where does it point to? RAX is this value here, which points to, so this is the second pointer. So this pointer here is the pointer to the new inputted value, and RDX points to the head of the list. Okay, so now what we're doing is we're reading the date out of the head of the list, and then we're reading the date out of the new entry. Okay, so we can see here, that's the date from the first entry, that's the date from the second entry. Okay, so we are now calling compare date. So we're passing two 64-bit integers into compare date, and it's going to return a value that indicates whether one is bigger or smaller than the next. Now I'm going to skip over this call, and remember that the value returned in EAX is going to tell us, hopefully, which direction things are greater than or less than. So Rax says 1. So what we're saying here is, with RDI pointing to what Rax was, which was the second pointer, and RDX being the first, excuse me, that means that this value here being 1 day after the previous one, we can see that the value of 1 was returned, which says that the head of the list is actually less than, or I should say, the new element is greater than the previous element because of the day value. And I'm sure if it was 3, it would be because of the year value. And we can check that in just a minute. Anyway, so we check that and we say, you know, do we have to iterate basically? And it says, yes, we do need to jump. Now let's quickly go back here, compare date, jump to this location, and we'll do some more accounting by the looks. So this is going to be classic pointer shuffling, right? So what are we getting now? Rax points to the head of the list. We then extract the next pointer, which should reference DTOP. There you go, there it is there. So we pull out DTOP and we store that back into a local variable, and then we increment our counter. And then we compare that again to DTOP. Right, so we can see that. Where are we? See how we've gone from here, we've incremented our loop, and we've gone back up to here. And we are now comparing to DTOP again, okay? So, at this point, obviously we've reached the end of the list. So this should be our terminating case. Now let's have a look at what accounting is done here, because this next step will give us an idea of how and where things are inserted. Okay, so Rax and RDX. Rax points to, this pointer is the new value we're inserting. RDX points to the terminator. Okay, it points to DTOP. So, that's stored in, we are now storing RDX, which is the terminating value, into what would be the next pointer value, which is the terminator. So it looks like the head of the list is going to remain the same, and we're inserting the second value after, right? So the next pointer would contain a reference to the new value that we've inserted, and the head will remain the same as far as the terminator in the other direction. So let's have a look again. We're extracting 2 values. Right, so now what we've got is RDX points to our first element in the list, RAX points to the second element. And then what we're doing is we are writing into the third pointer of the new element a reference to RDX, which is the first element, okay? Interesting. Okay, so to try and get this in your memory, you basically have, remember we've got our four 64-bit values. We've got the date, we've got a pointer to the string, we've got 2 pointers which are like next and previous. We're not quite sure which way round they are at the moment. What's happening here is we are taking the value that is in RDX at this point, right? So RAX is the new date, the new entry that we've added, and RDX is the first entry that we've added. And we have written the pointer that is RDX into the third of those 64-bit values for the new element. So the new element now has a pointer to the first element, right? And I would assume that this next little block of code is going to do the opposite. So we can see here that Rax points to the head of the list, RDX points to the new one, and again we are now storing in the, sorry, this is the third pointer. We are pointing that value to the new element. So what looks to be the case here is, out of the 4 values in our sort of metadata structure, we have the date, we have a pointer to the data that contains the diary entry, we have a next pointer, and we have a previous pointer. And what we've just done is we've written in the first case, we've got our next pointer pointing to the new entry, and previously we wrote the previous pointer is now being referenced towards the first element. So we do have what appears to be a doubly linked list with a sort of hard-coded terminator at the end of it. So the test EAX, blah, 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 making sure the comp date call is greater than 0. Yeah, exactly. So let's go back to here. what it's doing here is it's saying, do we effectively get a non-zero result, right? So this is, I think test is a logical and. SM test is logical and, I think. Let's just make sure. According to the documentation, the test instruction performs a bitwise and on the two operands, and all it does is modify the flags, but the result of the and operation is discarded. So it'll set the sign flag, the zero flag, and what's PF again? Parity flag. So they're the flags that it's going to modify. According to this documentation, the overflow and carry flags are set to 0, and the last flag is undefined. So we're really interested in 3 flags: sign, 0, and parity. Okay, so the test effectively does the logical and then we're saying jump if greater than. So what we're looking for at this point is we're iterating through the list, and we only go to the next value in our loop when the new entry's date is greater than the one that we're looking at. Right? Does that make sense? And does that answer your question? Yeah, cool, awesome. Good question, mate, thanks for that. Hey, Parity. How you going, dude? Okay, hopefully this is making a bit more sense. We're starting to understand what's going on. This is just a classic sort of insertion into a doubly linked list. The difference here being that we're not actually using null terminators for the head and tail of the list. We've got this dtop variable, which obviously we're using to point to both the head and the tail of the list. Going well, just upgraded HomeNet to, ooh, man, 250 down, 100 up. Gotta be happy with that. Hope it performs. So yeah, interesting. Okay, so with that out of the way, what else are we doing? We're doing a little bit more accounting. We are writing, yes, we are updating the terminator pointer so that the terminator's previous pointer points to the new entry. Okay, so we can see here we are storing rdx, which is a pointer to the new element, inside racks plus 18, which is, I'm calling it previous rather than next, but I guess the direction is not that important. It could be left and right, blah, blah, blah. But the way I'm seeing it is, given that we are looping through the linked list in a positive direction, we're making sure that it's actually aligned based on date, that the first pointer is the next value in the list, and the last pointer points back in the opposite direction. Okay, so EAX is probably going to be 2 because that's how big the list is now. Okay, now I'm going to do one more loop through this just to make sure that things are doing what I would expect. Well, let's go input date. We'll go 1980 this time. 12. So we've got a bit of a difference in the dates. Content size 256. Please write what happened. I'm just going to mash the keyboard. Okay, so we should at this point see that this value, we've got the head of the list here, and we've got our new element here in RDI. Okay, so moving through our loop again, are we looking at the terminator? No, we're not. So I think it's probably fair to say at this point that this data 6020D0 is, I'm going to call this the list head, because that's clearly where we're starting our iteration. We've got a pointer to the head of the list that's stored in a global variable, and that's what's referenced to begin with. So the head of the list is the very first element in the list based on the date. So the element in the that has the smallest date value, it should be at the head of the list. Okay, so have we reached the terminator? No, we haven't. Next, we're going to go move. We're going to pull some metadata out and we're going to do a date comparison. So here are our two values. We know that we're going to come back with the year. So I'm guessing that EAX is going to contain 3. Yeah, there it is. It's telling us that the year is the differentiator. 12/12/1980 is my birthday. Ha! Unfortunately, no, that is not the case. I'm older than that. I am older than that, trust me. Righto, so jump, then if greater than, yes it is. So we're going to end up looping. We're going to pull out the next pointer to the element that's the next in the list, as we can see here. There's our next pointer, which points to the 2nd of January, 1970. And we're going to do the same thing again. Get that date value out, increment, and compare. So have we reached the terminator? No, we have not. Right, so what happens now? We're pulling out 2 more dates to compare. And here you can see the 2 dates that we're comparing are the 2nd of January 1970, i.e. the date that was in the second element, and the date in the new element, which is 1980 12/12. Bandit! Wow! Bandit. Nice to see you, sir. I'm honored by your presence. We are in the presence of greatness, ladies and gentlemen. Presence of greatness. I'm now semi-starstruck and I'm probably going to end up sucking more than I did to begin with. So, yes, nothing to see here, Bandit. Hope all is well with you, dude. I appreciate you dropping by and saying g'day. Okay, so another classic date comparison. That's going to come back probably with another +3. Another +3. Saying that the year is different, but again, we've got to move to the next element. And the jump is taken. We iterate to the end. We check to see whether or not we've reached the terminator. And in this case, we have. So here we're going to go through the process of adding an element again to the end of the list. Righto. So there's nothing new going on here. What we might do though, just to demonstrate, is we are going to reference, where is that? I should just type this out again. XQ4QX. Where is the pointer that I want to see? It would be in, it's not there at all. Let me just go back here. So the list head is in this location. I'm just going to copy this address. Okay, so we can see dtop +16. Okay, so this is actually just a direct alias into the next pointer for dtop, and dtop being the terminator, okay? All right, so let's go back and go 4QX, and we'll just reference this pointer here. So I just want to make sure that what we think is going on is exactly what's going on, right? So here's the first element in our list. The first element in the list contains the date 1st of January 1970. XS of this should be the first entry that we put in, nothing happened. And then we've got these 2 pointers. We can see that the previous pointer is the terminator and the next pointer contains, whoops. Is that what I meant to do? Yeah, it is. Why did that not do what I expected? That's fascinating. Something changed and I don't know how or why. Someone who knows more about GDB can help me there. Why all of a sudden am I seeing that? What did I do wrong? What did I change? That command there produced these 4 pointers before, and now it's not. I don't understand why that's the case. Anyway, point is that this value here, we can see, contains, I wonder if we can use print. Can we dereference that? Yeah, we can. I'm going to quickly look at the GDB documentation again to see why I'm doing this incorrectly. Giant words is definitely 8 bytes. According to this, you can examine memory for several formats. Use X command to examine memory. These are all optional parameters. The unit size. We want giant words. That's exactly what we want. Q for, oh no, it's G. That's my problem. There it is. Go figure why this one worked. Okay, so, sorry, back to where we were before. The head of the list contains the date 1st of January, pointed to the string that we've looked at here, nothing happened, and pointed to the next element in the list, followed by a pointer to the terminator. So that's the previous pointer, this is the next pointer. We're now going to do the same thing with the next pointer. And you can see the date is the 2nd of January. And this value here has something else, something happened here, great. And then the third pointer, you can see that the next pointer points to the terminator and the previous pointer points back to the one before. And the string stored in here is the mashed keyboard input that I had in the first place. Okay, so hopefully that will clarify things just a little bit. You can see that we are actually chaining a doubly linked list, and it's got a head node, which is a terminator, with a hard-coded value somewhere in memory that points directly to the head of the list, which is the first element with the smallest date. Okay, so what would be interesting here? I would assume. I mean, it doesn't look like there's that much happening that is too exploitable based on what I saw, except for that one element in where is it? It's not insert. It's called. It's not find. What was the name of that function again? I can't remember. Get inline. Here we go. This was it here. This thing that reads one extra character. So that is interesting. That is interesting to me. I get the feeling based on, I'm just going to speculate a little bit here, but if we're able to do some sort of standard heap kung fu, so to speak, if we allocated some blocks of information, if we allocated 2 blocks side by side, and then we freed one, then maybe we could, maybe freed 2. If we could reallocate the same area, then we would obviously encompass some pointer metadata. But we may also be able to overwrite the very last byte, which contains metadata for the next element. But that's only a single byte that we're modifying, right? Jeez, mate, put the guns down. I don't have guns. I'm just a dweeby nerd. Leave me alone. Leave me alone, Dan. Don't be nasty. Teasing me. Don't make me flex on camera. Okay, so one thing that's clear though to me is we need to find a way of probably getting a heap pointer. And so the first thing that I'm interested in, I'm not going to focus on this overwrite to begin with, because I think that's clearly something that we need to care about. But I'd like to know how we can get access to the content of a heap pointer. That's what I think we should focus on here. And given that it's nearly 10 o'clock and we're close to 2 hours in, it's about time we did something kind of exploity. Hey Parody, which CTF? So I've got this open in my web browser. So it is from Tokyo Western's MMA CTF 2nd 2016. And you can download it from this location here. Okay, if you decide you want to play along or beat me to the punch, either or. Okay. Now, what I'm interested in next is what happens when we delete stuff. So I would assume that there is there you go, there's a remove function. And remove is called in delete entry. So once we've done delete entry, we read the date, we find the pointer and we pass in the pointer call. That's the pointer to remove. We pass that into remove. The remove basically will go through. I assume it's going to do the classic unlinking process. It's going to get a pointer to the current element and it's going to get the 2 pointers for next and previous and point them at each other and then free the current node. That's exactly what I would expect. Hey Lurker, you gotta stop pimping that, man. You're gonna annoy people. Me included. I appreciate you wanting to garner support for me though. Thank you for that. Does anyone have any questions on what's going on so far? Am I being clear enough with my rather verbose thought processes? What I'm gonna do now, I'm actually gonna delete the middle element and I wanna see exactly what happens. So let's do it from this point here, copy address. So I'm just going to continue using the current session. That's BP on that address. Oops, not BP. I'm getting my wires crossed. Break. And now I'm going to continue. Let's go. Let's call show. There you go. We can see all 3 of them. For some reason, I've got to add a date. So let's do that, and there we go, something happened here. So we can see that there are 3 elements in the list. Now I'm going to delete that element. Okay, we've hit our breakpoint. Let's see what happens. It's gonna be, I'd be very surprised if it was anything more than a classic unlinking. Okay, so what's RDI? RDI points to the element that we're looking to remove, strangely enough. So that's stored in local variable. Okay, then what do? We're basically saying, is it null? Okay, so the first thing we're doing here is, are we removing a null pointer? Clearly we're not. So here we go, if it's null, we're going all the way down here and just saying return 0. Okay, so clearly we're not removing a null pointer in this case. So we can assume that we're going to skip that. Let's widen that up a little bit and reduce the noise. Jump is not taken in this case. So what are we doing next? We are comparing the pointer that was being given into our terminator. Okay, our terminating pointer, the global pointer. And in this case, clearly it's not. So we're not going to be doing that either. Now going back over here, what happens? Are we doing the same thing? Yeah, so if it's dtop, there you go. You can see there, it's doing exactly the same thing as to whether or not we have a null pointer. So if we free up a null pointer or we're trying to free the terminator, in both cases, that's not going to work. It just bombs out and returns 0. So again, that will not take the jump, or it will take the jump, and instead, well, let's extract a couple of pointers. So Rax contains a pointer to the element we're deleting, and then dereferences itself to get the previous pointer. So here you can see this is the pointer to the first element. Yep. And then here we're going to do the same with IDX, and this will point to the next element, right? There you go. So Rax points to previous, IDX points to next. And here you can see we're storing the next pointer in the value of the pointer for the next element in the list over the top of the next value in the previous element. So yeah, this is classic unlinking. This is removing 2 pointers, pointing 2 pointers at each other, and then freeing the element in the middle. And this will be the same with the previous pointers here. So racks points to, what is that? That's the next element. And RDX points to the previous, and then we're doing exactly the same thing. Okay, so that would mean that when we look at this element here, oops, 4GX. So if we point now to the very first element in the list, you can see that the next pointer points to the third element, the one that has the date that is the 1980 1212, right? So if we go X4GX of this, there you go, 12th of the 12th, 1980. So we've removed the current element from the list. And then what are we doing here? We're getting we're getting the pointer to the string. Here we can see something happen here. So the second element in our structure, which points to an allocated area of memory, that contains something happened here. And so what are we trying to do? We need to go, that's going to free that up. And then it's going to free the pointer itself up and return 1. Okay, that makes sense. So now when we show we're iterating over the list, there's only 2 elements. Okay, so that's fairly classic, right? No surprises there. We are doing some kind of unlinking. All right, so what we need to figure out now is how can we abuse what we've done so that we can somehow extract some pointers. So if we looked at this, let's draw a little bit of ASCII art, perhaps. What do you got here? Nothing but like a pro level hype man. Yes. Maybe I can use ASCII flow. Maybe this will help. If you guys haven't used ASCII flow, you absolutely should. Come on. This is so cool. Righto, so we can draw some boxes. So we want to make it so that we can construct, when we first add a diary entry, we get basically a metadata block. And then once we specified a bunch of information that we want stored, it allocates another block. Is that the order that it's in? So this thing here, how do we punch in text? Metadata. And this will be the content of the diary entry. Okay, based on what I'm seeing, right? So again, let's quickly go back to register entry. So we get the date, we then allocate 20 bytes, sorry, hex 20 bytes, and then we allocate another however many. So they would be side by side. Okay, so we've got the metadata, and that is followed immediately with the content of the diary entry. Do we have more questions? No, we don't. So we've got the content of the diary entry. And then again, if we add more, we end up with, oops, we've got more metadata here, and then whatever the content of the next diary entry is. So this metadata, content of the next diary entry. Okay, so we need some arrows. Inside the metadata, oh, actually we should probably have a terminator, right? So let's do this. This is basically what the terminator contains. The terminator's previous pointer will point, oops, yep, I can. So let's go out this way and then up this way. So that will point there. This will point out to here, up to this metadata. And then by the same token, there will be a pointer that comes out of the metadata that goes in this direction and points back here. And same story with this. Okay. They're supposed to go the other way, but you get the point. So let me just add some metadata here to Terminator. And this would be next, and this would be Rev. I don't know why that's upside down, but anyway, not that it really matters. Okay, so we've got this block of metadata here, which is the terminating area, and that points to the start and end elements of a list, right? We also have some metadata here that points this in this direction, and some metadata here that points in this direction. Okay, so you can see that everything's kind of referencing each other. This also points here, this also points into here, but there are no references from the content of the next diary entry. So here's what I'm thinking. Okay, so this is effectively one logical block. The metadata and the diary entry are pretty much back to back. So if we're looking at these pointers here, let me just see if I can. We can scroll back a little bit. Okay, so we can see, for example, that this pointer, which was the first element in our list, contains another heap pointer at 4B030. Okay, so you see how we've got 008 is our current pointer, and 030 is where the string is stored. So that's hex 28 bytes difference. Now, given that we know the size of this metadata here is hex 20 bytes, what that means is that the metadata associated with the pointer itself that's allocated from the malloc call has 8 bytes prepended. And that's probably just an indication of the size. All right. So, but what we're effectively seeing there is that we know that we've got two contiguous blocks. We've got the first 20 bytes of metadata followed by 8 bytes of heap metadata followed by whatever it is that we've got as our diary entry. So if we free something up, then we're basically in a position where all of that information is freed, or I should say that area of memory is freed. And if we can allocate chunks that are of a similar size, then we should be able to write, I should say, to take up the same space on the heap next time we allocate that object. Okay, so if we freed 30 bytes and then we ask for another 30 bytes, we should basically get the same pointer back. Now, what I'm thinking is, in this case, if we had a scenario where we had like, oops, that's not what I wanted to do. Let's say we had metadata and a string content, metadata, string content, okay? Metadata, string content. If we freed up, for example, let's say we were able to free up this middle one, and then we freed this one up, right? And then we allocated metadata again, oops. We allocate metadata again but we like have an enormous string value here. Okay, that hopefully, like, we fit that within the same area of memory because the sizes are the same. But behind the scenes, because the content of the memory itself hasn't been overwritten, somewhere in this region here there would be some next/prev pointers that hopefully we could somehow read. Now, if this metadata here, like I said, this metadata will contain a pointer to this area here, which is the string that contains the diary entry. If we could make it so that the diary entry overlaps with some old metadata, some space where the metadata used to live from a previous entry, and then all we would need to do is sort of fill in the string with, let's say, A's all the way up to where we know the address lives in memory. And then we could say, hey, can you show us the content of this, this diary entry? And then with a bit of luck, when it tries to print it out, it actually prints out all of this content followed by the pointers, and therefore kind of coughs up a heap address in the process. Does that make sense? I've still got people following along. According to Twitch, there are 38 people here watching. So hopefully someone's following along and can validate my thinking. So if that makes sense, like what I'd like to do is come up with a way of just making it so that the diary entry string overlaps what used to be diary entry metadata. That's what I think we need to be doing. So that would mean, thinking out loud, we know that we've got a 32 byte metadata chunk. We've then got an 8 byte block of libc metadata that's associated with the allocated chunk, followed by whatever it is that we're doing. So I think at this point we're going to have to start automating some things. So what I'm going to do is I'm going to go p.send line. We're going to start with registering a new element. Then we're going to say it's going to request the input data. In fact, I should probably read some crap in, shouldn't I? So let's go p.recv until exit. So that's me just saying I'm going to read. Oh, actually, we should read all the way up to here. So the end of the menu. Yeah. And then we're going to send line 1. So if we do that, if we say register, in the first instance, it's actually not going to really bother us, is it? In fact, we don't need to worry about that until we are going to read the next menu entry. So we'll just say send line 1. It will say add entry to diary. We need to give it a date. So let's start with 1970, 06, just the middle of the year. Okay. Yeah, does that make sense? Input date. I'm just changing this so that it's easy. Then it asks for content size. So p.send line. Now, let's have a think about how big we want this to be. We want this to actually be fairly small. So for the first, I'm going to say 3 of these. We'll just make them 32 bytes so that they're the same size as the metadata. Okay. And that should be fine. We want to do that 3 times. And then I'm going to go, let's put some constants in here. Metadata size equals, and let's make it look like the hex. So here what we want to do is go dot format metadata size. I know it's unnecessary to go to this length, but I like to make it legit. So we're going to add some things sort of back to back, and we'll separate them by, let's separate them by a year, just so that we've got that option, right? Let's go start year equals 1970. Okay. Oops, don't need to do that. 0. I am hopeless. Format start year. All right, now what I'm going to do is I'm going to do this for a number of times. So let's go for X in range. We're going to do it 3 times. That's going to be start year plus X. So that means we should be able to create 3 entries. Now, after we've done the size, what do we need to do? We're going to go 32, and then it says, please write what happened. So we're going to rec v until that. And then we're going to send p.send line. Let's go ord of a plus x, and we'll char that. And we'll do that how many times? Metadata size times. So we're going to fill it up. The first time it'll be all capital A's. The second time it'll be capital B's. The third time it'll be capital C's. And so that will hopefully give us 3 entries that we can play with. Okay. Now let's just quickly see if that works. Let's see what happens. Ooh, we've got breakpoints. I should probably clear the breakpoints, eh? Because I'm actually not interested in pursuing the breakpoints at this point. So, yeah, let's just get rid of them. Okay. All right, that's interesting. So if we type show, have we got 3 entries? We do, and they're all separated by a year. So if we show this one, we should see A's. Ooh, followed by, look at that. That's it. We've already got some kind of memory leak there, which is cool. What happens if we show the second one? B's. And then C's. Okay, cool. So what I think we're already seeing there is some kind of leak of memory. Although I might actually be wrong. Let's just quickly go and ASCII. Let's just have a quick look to see. Where are we? We're on the open parenthesis, yeah? Because that's what we're seeing spat out on screen. Where is it? Can anyone see it? Okay, so 28 or decimal 40. Okay, that makes a lot of sense. Because if we, like hex 28 is hex 20, the amount that we're asking for, plus 8 bytes, which is the size of the metadata. So clearly what we're seeing is heap metadata being leaked. So that's from glibc, if that makes sense. Because let's go back to ASCII flow for a sec. Remember that on the heap for glibc, we end up with basically this, okay? So we have the size stored here, I believe, followed by memory to be used by application. And when malloc returns, what you end up with is a pointer to this location. Let's go this way. Pointer to this location here. So the metadata comes before it. Now in our case, this area here is 32 bytes, or hex 20, and this is another 8 bytes, so hex 28. So the value of hex 28 is being written in this location as an integer, which means the very first byte, because of it being little endian, is 28. And as a result of it being 28, when we print out the content, as shown here, the ASCII value of 28, which is an open parentheses, is actually being rendered to screen. So that's very interesting, I think. Now, we're now in a scenario where we've got 3 chunks. 1, 2, hang on, let me redraw. Might clear some of this gunk out. Let's redraw. We have 3 chunks like this, and they're all pretty much back to back with heap metadata between them. 2, like this, yeah. 1, 2, 3, 4, 5, 6. Now what I want to do is delete these second two, and then reallocate one that covers like this whole area. Right? That's what I'm going to do now. So we're going to delete the last 2. So 4x in range 3. Let's have a look at what happens when we actually interact with this before we attempt. So when we try and delete, this will be range 2 actually. I'm going to delete the last 2. And it doesn't really matter which order that we do it in. Excuse me. So we're going to get rid of these 2. It says please input a date, so we don't really need to. We can go send line 3 because we're using the delete function. We're going to go start year plus x plus 1 because we're only doing it twice. We want to delete the last 2. And then I don't think we need to give it anything else. From there, it should just say, ooh. This is interesting. Looks like we've got a bug. Rex keyword pointer Rex. Ah, yeah, okay. Now remember how inside our insert entry, where is it? Where's that function? Get inline. We're reading 1 extra character, which would include the new line that we're passing in. So instead, I don't want to. This is clearly causing a problem because we've got a crash. We've managed to screw something up, and I think it's because we've given it too many characters. So instead of metadata size, we're going to go metadata size -1. Let's do that. Okay. And what I'm going to do is I'm going to rerun it. Okay. Oh, looks like we've got 2 deletions done already. So if we go now and show, there should only be 1. Okay, cool. So that actually did what I wanted it to do. Who is this? Are you a hacker? No. No, I'm not. Okay. We're just playing with the capture the flag challenge, that's all. All right, so we can see that there now. Now what we want to be able to do is we want to allocate some memory so that we cover off the same amount of space that we had before with the metadata associated. So we know that we've cleared out 4 blocks of 28 bytes, and each one of those blocks has 8 extra bytes, so hex 28 bytes. for each one of these blocks. Okay, except for the first one, because the first one will have that allocated and the second one will have it allocated too. So we're looking to allocate a block of memory that contains the dire entry text. So that will be, this is what we can't help, that'll be the same. There'll be a block again in here that's worth 8 bytes, which we can't really see, but we want it so that it is 32 bytes plus 32 bytes plus 32 bytes with 2 chunks of 8 bytes in the middle. Okay? So that means we're going to do this again. And we're only going to do it once. So we're going to recce until we get back to the menu again. Then we're going to insert. Now this time, it doesn't really matter where we insert it. But what I'll do is, actually I'll leave it like that and I'll say start year plus 10, just so that it's way off in the future. This time we're going to have metadata size, it's times 3. Okay, like we said back here, we've got 1, 2, 3 lots of the metadata size. And then for each one of those, we want 2 lots of 8 bytes. So that would be plus metadata size. No, not metadata size. Yeah, just 2 times 8 bytes for the heap metadata that's associated with it. Okay? And then from there, we want to be able to write over everything from the start, which would be here, 32 bytes. Hang on, let's have a think. We probably don't even need to write a full 32 bytes, do we? Because as long as we get to here, we can start. Oh no, we do. Yeah, we do. We want to write all the way to here. We want to overwrite the 32 bytes that we were allocated, followed by the 30. We want to skip the size. We want to skip the date. And we want to skip nothing else. Okay? Yes, that's what we want. So remember, our metadata block is made up of 4 things. We have the date. We then have pointer to data. We then have p next. And then we have p prev. Okay, now what we're interested in, like we know that this is 8 bytes in here. So we want to skip over this section, which means there's 8 bytes we want to skip over, but we don't want to tarnish this pointer here. Okay. Say it with a straight face. No. Yes, that's apparently the proper term, bandit, apparently. Jimzo, I wouldn't say that I'm one of those. Yeah, you can watch the stream later, mate. Oh yeah, as Blue Pill just mentioned, I do archive stuff up on YouTube. And so once I'm done here, I will push this stuff to YouTube for you all to enjoy. Anyway, back to our math. So we know we've allocated this space again. Okay, I know I'm making a bit of a mess of this ASCII diagram, but we want to skip over these first 32 bytes, followed by the next 8. So 32 plus 8. Okay. And this time we're not going to send line, we're just going to send. We'll go all the way up to and including those 8 bytes, which would overwrite what used to be the date. And then from there, we want to go through the process of showing the content to see what it spits out on screen. Okay, so let's quickly do a bit of math here. So I'm going to rerun this. Please write what happened. Oh yeah, I need to actually write that, don't I? I didn't do the math. What a fool. Okay, so we send out of size. We're gonna have to calculate this again, aren't we? So size, and then here we're gonna go p.send. Well, let's just do z's times by size, and then we'll go interactive. Maybe we need to go p.recv until. Let's do this again so that we get the next menu, and let's see how that goes. Ooh, okay. So if we now type show, what do we got? We've got 2. Okay, so that's cool. Let's have a look at what happens when we try and spit that out. Ooh! Okay, so that's already interesting, right? That to me is interesting. It looks like we are leaking something. I don't know whether it's a heat pointer or not, but it's definitely something. Ah, you want a YouTube video? Link youtube.com/ and there it is. Alrighty. Okay. All right. So now I'm not sure whether this thing that's been leaked here is actually useful to us or not. I'm guessing that I've probably got it wrong. And let me just have a think. That's F11. I'm thinking that I need to override another 8 bytes. So because the size, hang on. We don't want to overwrite the full size. So that's definitely not what I'm looking for. What we're looking to overwrite here is we want the first 32 bytes that we expected, followed by the 8 bytes for the date. That's what I expected. Okay, so let's run this again. Let's see what happens now. Ooh, okay. Okay, so that's interesting, yeah? See how we've got this, XB4, X70. All right, so now what I'm gonna do is we're just gonna set a breakpoint. We're gonna break in here, and I'm going to look at the content of the list behind the scenes. So let's quickly go back to where the DTOP address is. Going back, be in here somewhere, won't it? Get online, registration complete. It's not what I'm looking for. Remove DTOP. Here it is. Copy address. Okay, so X4QX, boom. Okay, so actually we would want to subtract hex 10 from that. Nope. No, we wouldn't. That is definitely right, DTOP. Okay, so this is our head pointer. Okay, so if we want to have a look at the content of the head, it points to next. Now the question here again, like the assumption that I've made here is that we have actually been reallocated in the spot that we were expecting to be reallocated. So we need to check that. But let's have another look at this next pointer. So the next pointer points to the terminator, points to the previous. Now this is already interesting. because it looks like it's at least in a similar region, right? So if we look at, what I want to see, a D word at this location -8, 121 bytes. Apparently that's what this would be, metadata size times 3 plus 2 times 8. That doesn't make sense though, does it? Yeah, okay, so let's go QX. 5A, 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 5A. That's definitely Z. Z, 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 Z. Isn't it? Is it? Yeah, right, there we go. So that certainly contains the string that we're looking for. Let's do a few more. Okay, all right, so this is interesting. So we've overwritten almost everything that we want to. But this thing here, that looks like a date again, doesn't it? That's a date. So we need another 8 bytes overwritten so that we can get to this value here. But look, that's definitely a leftover heap pointer. Okay, so if we can add another 8 bytes here, oops. If we add another 8 bytes, then these Zs should fill up and overwrite this value, and this heap pointer here should be leaked, which is exciting. That's very exciting. What do you think? Is it just me that's excited? I mean, I don't care if I am the only person that is excited, but you know, I think it's exciting. All right, let's go again. Show, oops. Show me the pointer. There it is. Okay. So we are at a point now where we can actually leak heap pointers. That's interesting. Get excited. I'm feeling the love, boys and girls. Feeling the love. Thanks very much. I think this is a win. So we actually have the ability here to read heap pointers. I'm excited about that. But what can we do with it? At this point, what can we do? We have the ability to read pointers that allow us to determine where we are in memory, heap-wise. Right? So, if we have the ability to do that, we now need the ability to do something else, don't we? We need the ability to do something else. In the classic sense, when you're attacking linked LinkedIn. I wish someone was attacking LinkedIn. No, don't attack LinkedIn. Someone's attacking doubly linked list. You end up with a scenario where you kind of get a right what where because of the unlinking process. And I get the feeling that's why we saw that crash before. So if we have the ability to, let's say, we have the ability to change 1 byte somewhere, don't we? Because we can read beyond what it is that we are writing to. So, with that in mind, what can we do? We can overwrite 1 byte too many. While you guys think that over, I am going to quickly do something else. recv until, maybe we need to, let me just, I'm doing that twice because I think I've missed one. Yeah, okay, that's better. I have clearly missed one. Now what I want to do is let's go let's go offset equals this. The until. So then we can reuse offset and we can say p.send, we want to read, so that's 2. We want to send line 2. We'll, once we've sent that, we need to send in this one that we've just created. And then from there, we want to recv until we get to z times offset. And then the next however many bytes we have, we know that that's going to include, what is it? What is it going to include? There's going to be one, in fact, we don't even know how many bytes that's going to include. Okay, so we're basically reading all of the bytes up to the start of the address, right? And so then what we want to be able to do is we want to read, so let's just go data equals p.recv until 1.register. Okay, so now we know that it's going to be reading all the way up until this with a new line in front of it. In fact, 2 new lines. There's one there and there's one there. Okay. And then I'm going to go print data just to see what it says. That didn't look too helpful, did it? Print data.encode x. Okay, do we have anything interesting here? I think we do. There it is, D0609607. 78 F7 new line. So there you go. That's what we need to strip off the end. Okay, so recv until that, we want to chop off the last part of this. So if we get rid of this, we go, we'll call this the tag. Okay, we want to receive until the tag, and we want to chop off everything up until the length of that tag. Data. So then we go print the pointer is, and then we just sort of add hex. Actually no, because that's a string, we need to unpack it, right? So that's the data. We can say heap pointer equals whatever the data is. We need to make sure that it's padded to 8 bytes though, right? Can never remember this. Python pad string. Is it .ljust or something like that? It is .ljust. Yep. So we want to go data.ljust and we want to give it nulls. And we've got to make sure that it is 8 bytes, right? And then we can pwn.unpack a 64-bit value. And from there, we should hopefully get a a heat pointer. Ooh. Ooh, let's have a look at that. That's pretty cool. If that's exactly what we're looking for, I'm going to be quite excited about that. VM map. So, according to this, we have, what are we looking for? 7F65BB, 7F65BB 93E0. So, ooh. Okay, so there's two things that are really interesting about this. The first is that we've definitely got a valid heat pointer being spat out here. We've got 93E0D0. Use 93E0D0 fits solidly in this mapped area here. What's crazy about this though is that it's read write X. Okay, so am I missing something here? Is there a custom allocator? Because I'm confused. Malloc. Oh my god. There's a custom allocator in here. How did we miss that? I'm gonna blame, let's go. I'm gonna pick a name at random. Lord Fliplo, let's blame you. Let's blame you for not pointing out that I missed something. It's all your fault. Holy shit, how did we miss that? How did we miss that? Look at this. Malloc. Okay, so we've got, what's this, a global pointer? H-top. Oh man, so H-top is clearly a pointer to a custom heap. So, let's have a look what's going on here. That is, it looks like we've got some metadata. Oh, look at this nmapped buff. Really? This will teach me to not actually analyze more of this stuff before I start diving into code. Unlink free list, check this nonsense out. Okay, so I've made some assumptions based on the fact that I was expecting like heap metadata to be a certain size. And obviously with my assumption, I was not only wrong to make that assumption, but what I was talking about while making that assumption was also incorrect. So, clearly, we have the ability to get a heap pointer out. But we're not even using malloc and free. So, look at this. Unlink free list, link free list. Wow. This is just classic old school allocator mistake. So we have a right or aware opportunity by attacking the custom allocator. Wow, I'm pretty amazed by that. Init heap. You gotta be kidding. Memory map, there you go. So call mem map. Far out. What a thing to miss. Let's just have a look at what nmap takes. So nmap address, length, protection flags. So clearly prot's going to be, what is it, 7? Is 7 read write X? I'm pretty sure it is. What were we looking at before? Sorry, wrong window. So third parameter EDX is 7, read write X. Holy pants. So we're basically allocating one massive page, one page of data. We don't care where it is, and we're saying make sure it's read write X. That's pretty epic. Okay, so but what's interesting about this too is we've got this in SECCOMP. So what's going on here? For those who aren't familiar, SECCOMP is a way of preventing certain syscalls from being allowed within the application. So usually you'll see it used to prevent you from being able to do things like execve and things like that. So let's pretend that we were at a point where we were able to write, do a write what where sort of thing, and let's say we decided to overwrite the pointer for exit in the GOT to point to the area of the heap that we control, and controls actually pass even though it's read write X. We would need to be in a position where the shell code that we then execute is able to do more than just what the SECCOMP limitations have done. Yeah, interesting. Very interesting. Okay. So my guess at this point is that this SECCOMP thing is going to make it painful. But at this point, we really want to get to a point where we've got code execution. So we've managed to leak a heap pointer. What we now need to figure out is how can we abuse a write what where scenario, given that we effectively have a one byte overwrite. So what we need to understand is what that 1 byte overwrite is going to let us do. And so if we're able to overwrite the first byte in this allocator, then we should be in a position where we can say, well, we need to figure it out, don't we? Let's go back to malloc. Okay, we need to figure out effectively what the metadata of this custom allocator contains. If that makes any sense. You guys with me? Am I making any sense? Interesting having the binary open and idle to decompile watching you progress. Progress, for want of a better expression. All right. So I'm also quickly checking chats behind the scenes. It's probably where you can see the reflection in my glasses of Windows flashing, and you can't see it on stream, is because I'm only streaming from inside the virtual machines, so that all of the other potential OPSEC fails that I make along the way, such as passwords or someone trying to troll me with notifications, doesn't actually pop up and appear in stream. I'm learning slowly, very slowly. Okay, so let's have a look. We're 2 hours and 50 minutes in. We're able to leak a heap pointer. We understand that there is a custom allocator. We clearly have noticed that we have the ability to overwrite 1 byte more than we should. So, given the time, what should we strive for? Should we strive to get to a point where we consistently crash and have knowledge, and then we can put this on pause, and in a couple of days' time we can come back and do the next part where we take the knowledge that we've gained and we get code execution and then try to bypass what appears to be SECCOMP filtering? Because I reckon that's probably the best way to go. I know I seem to be breaking streams up into 2 parts of late, but I think, given that we've been at it for such a long period of time already, that would most likely be the best way to go. What do you folks think? See if we can get a consistent crash and go from there, because that's kind of what I'm thinking. I await your opinions. Anytime. I was about to go as I need sleep. That's a good sign. Kinda. Okay, so I'm now going to do... let's go then. So I'm gonna do another 2 of these things actually. Another 2 of these. Add year plus x plus 11. Oh, you come up to Brizzy, hey? It is a long drive, mate. Okay, so we're going to create 2 more, and then I'm going to delete 1. This time I'm actually going to go full metadata size for overwriting. And we're only going to get rid of 1, so that would be start year plus 11. And let's see what that does. I'm guessing visiting, because he moved from Brisbane at one point. Now let's just see what this does. Isn't this interesting, folks? Have you noticed something here? Check this out. You guys see it? So clearly, what we did with we added 2 more. And by overwriting that extra 1 byte, we seem to be in a scenario here where we're attempting to write 41414141414141 to a location that we control. So we do actually currently have a write where right here in unlinked free list, just like we expected. So instead of doing this, what I'm going to do is we're going to do the what's it called? Let's call this payload. Payload equals pwn.util.cyclic metasploit metadata size. I like using the metasploit thing because I just find it a little more easier to digest. Well, what do you know? See that? That's pretty interesting. Hey, we can see here that we've got 2 different locations that we actually control. So if I was to go, I know I'm kind of getting ahead of myself here because I'm not understanding why. I haven't gone into why the allocator causes these problems. But like I said, when you're attacking classic allocators with free lists, this write where thing is just typical. So no, I need to go code, metasploit framework. We need to go exploit. Pattern offset.rb. Actually, this isn't going to work, is it? No, just ignore that for a minute. Let's go. We know that we are writing 2. Let's go racks crash equals home.util.cyclic metasploit find, and we know that it's this value here, right? And then our dx at the time of crash is this. Now I'm going to print both of those, racks crash and rdx crash, before we go ahead, just to see which ones. Okay, look at that, 0 and 8. Interesting. So that would mean that we could say the payload equals A, followed by B. And we then can just sort of fill it with C's times, what should it be? Metadata size minus len payload. And there we should see when we rerun this, there you go, B's in racks, A's in RDX. All right. Bring gunships, knife fights. I'm always overthinking the problem. Yeah, man, that's exactly it. Hey. All right, so I'm going to be rather brazen, and I'm gonna push on and try and get code exec here. So we have the ability to write a value to a known location, and because of the way this works, we know that we can point directly to the heap. Yeah, we can point directly to the heap with our payload, which we're doing at these Z's. We can actually create a whole new one, can't we? Yeah, that's what I'm going to do. I'm going to create one more of these. And I'm going to fill it. But instead of metadata size, I'm just going to make this, you know, a decent size. And I'm going to go, we'll send hex cc times ox ff. So it's, yeah, anyway. Let's, actually we'll make it slightly bigger because we might need more shellcode space down the track. So we'll go 1ff. Okay, so that means we'll fill things up. We'll make sure that this is later down the track. So let's, I don't know, how many years later? 20 years later? Send that down the wire and then delete the one in the middle. And then at this point, what we can do is we can figure out where in memory with respect to the pointer that we know we have, whereabouts this buffer sits, and then we can do a got overwrite, which will hopefully tell us, like we know that exit is something that can be called just by bailing out. Oh, hey, Peleus, thanks for coming in, dude. How are you doing, mate? I think we'll get code execution by doing this, but we just need to do a couple of debug sessions at this point. All right, so first of all, I want to get the offset that we need, and we can do that fairly easily by crashing. And then we can say search mem ox cc. Righto, so it looks like that would be the first location. Okay, so if we did that minus what we know our heap pointer to be, then we know it's only F0 bytes beyond. Okay, so we can say, well, if we've got our heap pointer, we can say our target, we can say payload, no, shellcode pointer, else SC pointer equals heap pointer plus OX F0. Let's go, the shellcode pointer will be SC pointer. Okay, so now that we have that, so what I'll do is this pwn.log.info, so that comes out as something that's part of our information. And then once we've got to that point, we need to be able to write the value of, well, where are we? Let's cancel that and run it again. So the shellcode pointer will be out. Oh, did I do it wrong? I didn't save it. Shellcode pointer will be at this location. Okay, that's fine. RDX is getting written directly, so we want RDX, which is BBBB, to be whatever the heap pointer is going to be. So we need to go pwn.p64, the shellcode pointer. Let's run that. Is this making sense? Please tell me if it's not. Check it out. There you go. We've got our shellcode pointer. Bang. We are trying to write that to a known location. So what we need to do now is we need to figure out where in the GOT we can clobber some information. So how do we do that again? It's one thing that I haven't done or really made an effort to automate, and that is come up with a nice way of finding the entries in the GOT. So exit PLT is at this location. So we want to copy this address. So we want to overwrite the content of this address, right? So let's go back to where our, this code is a bit of a mess, I'm sorry, but exit GOT equals that address. So we want to be able to, now we can see here that the crash, the point that we're crashing is where we're trying to write RDX is being written to RAX plus 10. Now I'm going to run this again. Yep, RAX plus 10. So we want to, here, we actually want to write pwn.p64, whatever the exit GOT address is, but we need to subtract hex 10 because of the offset here. Right? Does that make sense? I don't know what's going to happen. Okay, so if everything goes to plan, when I type 0 here, we should hopefully get a breakpoint at the first CC in our payload. So, cross your fingers. Boom! We've got code exec. Yeah. How cool is that? So we've just abused a write what where in the half-baked poor implementation of free lists in this custom allocator, and we have the ability to execute code just by overriding the GOT and exiting the program. So at this point, what I should be doing, instead of going p.interactive, we need to go p.sendLine 0. And we can probably do another rec v until like that. So, okay, so we've definitely got code execution. Now comes the fun part, I would assume. I don't think it's going to end here. I think there's going to be some quirks, particularly with the SECCOMP. So, but what I'd like to do is at this point, instead of trying to dive into the configuration of SECCOMP and then trying to figure out how we can bypass it, I'm going to stop and we'll resume this in a couple of days' time. So, is everybody cool with that? Everyone's cool with that? I hope so. Hopefully you've learned something. I thought that was actually quite good fun. I might have overanalyzed some areas and underanalyzed other areas, but you know, I get the feeling that, I mean, getting code execution there was actually quite trivial. I reckon there's going to be some other quirks involved in getting a fully active shell in this particular scenario. So let's regroup in a couple of days. I'll aim to do it Thursday like I did last time. So 3 Killix. Yeah, thanks a lot, man. I really appreciate you sticking around and watching. I hope you enjoyed, and definitely hope to see you around. Hey, so I will get this stuff uploaded to YouTube like I do with everything else, and the lines are open for communication. If you feel you need to get in touch and ask me some questions and all that sort of stuff, the usual things apply. So reach out. Thanks again for giving me your time. Love you all, and I'll see you in a couple of days.